I will use a vegetation index called NDVI on multispectral satellite imagery to monitor the terrain around a strategic business unit, which, as you can observe, is surrounded by what appears to be dense vegetation. The analysis will help in the assignment of physical security around the site's perimeter. For this workflow, I have used 5 sets of multispectral satellite imagery acquired at different points in the year 2021, specifically in Jan, Feb, April, October, and November respectively. I have already derived the NDVI output over the entire extent for each set of imagery. The green zones are indicative of dense vegetation, while the yellow zones have sparser vegetation, and the white zones are completely devoid of vegetation. As you can observe, the vegetation density changes over the year. It does not remain constant. Thus, while planning the security manpower deployment around the perimeter, information about how the vegetation evolves around the site is the tiny pink box on the right of the output, how it evolves would be useful. Miscreants often take advantage of dense foliage, and having personnel manning these areas to foil the incursion attempts would be ideal. Now let me begin performing the time series analysis for these NDVI outputs. I am using European Space Agency's SNAP software for this workflow. After loading all the 5 images onto the tool, a graph will be created on the bottom left where you will be able to see the dates of the imagery acquisition and a line chart. The line chart will show how the NDVI is evolving for a particular pixel that my cursor is pointing at. Broadly speaking, values near 0 indicate bare soil, from 0 to 0.3 indicates sparse vegetation, between 0.3 and 0.6 implies tree cover, and above 0.6 is indicative of forest and dense vegetation. I'd like to emphasize that while I'm hovering on what is just a single output, the time series analysis is occurring on the same pixel across all the 5 sets of imagery. As I hover around the perimeter, notice how a trend can be observed. From October to March, there is a reduction in the vegetation density, whereas from March to September, it increases. While I have used low resolution satellite imagery, I can ideally use a drone with multispectral payload to capture it in much higher resolution and with much more frequency within a specified radius from the site's perimeter. Besides vegetation, terrain change detection can be done to also determine the evolving urban footprint, that is the built-up area of a city. For example, what you are seeing is the urban footprint on a cross-section of New Delhi, the capital of India. The footprint, that is the area captured by the white pixels, can be measured as well, so as to compare how it has progressed over different time periods. So in this comparison over an under construction university campus, you can observe that while 0.06 square kilometer of land was built up in 2015, it increased to 0.09 square kilometer, a 50% increase. One can also validate the output by comparing historical optical imagery, as I am doing here using Google Earth, as well as digitize specific features, example buildings as I am doing here, or let's say swimming pools, roads, and other topographic feature of interest to you through the use of deep learning algorithms. Besides vegetation and urban footprint, one can also use water index to determine the water body footprint. The avenues of performing terrain change detection are truly vast. Thanks for watching.